Oleg. Thanks, Oleg. Thanks, Xavier. Thanks, Boris. Thanks for putting together this meeting. I was actually looking forward immensely to have a meeting in Tours. And for the benefit of some young people who are maybe postdocs in Paris and who don't know where Tours is, I wanted to encourage everyone to visit this part of France, because it's the Loire Valley. It's very beautiful, and there are all these historic towns, Tours, Orléans. And the laboratory carries the name of Denis Poisson because he was born not far from Orléans, not shortly before the French Revolution. And importantly for my talk today, he was interested both in analytical and in numerical developments. So he published some papers on how to efficiently evaluate definite integrals at the beginning of 19th century. So yeah, please interrupt me with any questions. This talk is supposed to be very informal, very relaxed, not technical at all. And we had too many Zoom talks during this period of our life. So we probably cannot, I mean, me definitely, but you probably like me, we can't take any more technical Zoom talks. That's my feeling. So what is the Bootstrap? The Bootstrap philosophy is that we analyze a problem in theoretical physics, not from some microscopic equations, but from trying to distill some general principles and trying to apply those principles. And why would you be interested in doing such a thing if you know what the microscopic equations are? Well, you can imagine at least two reasons for doing so. The first reason is that these microscopic equations, even if they are known, they may be just too difficult to solve because your theory is strongly coupled, because you don't have any powerful symmetry like supersymmetry. There's no integrability. So, but you really want to solve this particular problem and not some other problem. So you want to make some progress, and then Bootstrap philosophy can help you. Another reason why you might be interested in doing something, and this probably is going to resonate with the talk by Karim Benaklin on 2 days from now, is that you might be interested not in any particular system, but you might be interested in the landscape of systems, and you would like to know what are the constraints on the landscape, what are the possibilities. So this is important if you think about physics beyond the standard model. You don't really know what is out there, but you want to know what are the all possibilities. So this is the philosophy, and well, this philosophy is not particularly new. So in fact, it has scored several very famous successes in the past. And I'll just mention here a few of them. So in the 80s, when people started working on the two-dimensional CFTs, so BPZ, Belayan Polycosm Rychkov. So these are the famous successes of the Bootstrap philosophy when they managed to solve the two-dimensional minimal models by not using the Lagrangians, which would be the microscopic equations, but using some constraints. And what are those constraints that they were using? They were using the Virasoro symmetry. They were using the crossing symmetry, which I'm going to mention later as well. And some other constraints, such as unitarity or modular invariance, also played a role. And then another similar success was later on in the solution of the quantum Liouville model and other related models, which are more complicated two-dimensional CFTs, and they were solved by using the same constraints as for minimal models, and by adding some guesses, some intelligent guesses from microscopics. So sometimes you can use microscopic description. You use it not to solve it, but to just guess what the right things are, and then you just incorporate the guesses. So that's one example when the Bootstrap philosophy was successful in the 80s. But even earlier example of this Bootstrap philosophy was the work in the I think it started in the 70s, continued in the 80s. It's about the two-dimensional integrable massive S matrices. So here we don't have a conformal field theory. We have a theory of particles, of massive particles, which scatter in 1+1 dimensions. And if you assume that this matrix is integrable, then it satisfies the Young-Baxter equation. And Zamolodchikov and others, they used it to solve many interesting integrable massive S matrices. And this work continues to this day. It's a very powerful approach. And okay, and in the recent years, there were more, so there was kind of, well, you can say, an increase in the number of examples where this Bootstrap philosophy has been successful, and including some theories where it was kind of surprising that it was successful. And the first example, and it's going to be the focus of my talk today, is the CFTs in D larger than 2 dimensions. So here, the constraints that you're imposing the conformal symmetry in D larger than 2 dimensions, which is a finite dimensional Lie group symmetry. Again, you have crossing. You might or might not have unitarity. If you do, the life is easier. Then you might or you might not have other global symmetries, like, for example, supersymmetry. If present, you can also impose it, because supersymmetry, it protects some quantities, but not all quantities. So if you want to study non-protected quantities, then you might want to use Bootstrap. And you also impose some gap assumptions on the spectrum, and then you usually get some interesting constraints. So this is what is known as conformal bootstrap, and I'm going to talk about it today. Some things I'm not going to talk about today, but which are under active development, are applications of this philosophy to other systems, such as, for example, general two-dimensional CFTs, not necessarily rational ones. We actually believe that there are a ton of, it's a belief that most two-dimensional CFTs are irrational and they cannot be solved by these tricks that BPZ invented. So they might, so the general belief is that if you want to solve an irrational two-dimensional CFT, then the Virasoro by itself is not much of a help. So this task is morally as difficult as solving a CFT in D larger than 2 dimensions. And here, for example, one interesting constraint that you might impose, again, that people try to impose, is modular invariance, but you have an infinite number of Virasoro multiplets. And this became to be known as modular bootstrap, and there was a lot of work on this. And another interesting activity which has started maybe in the last 5-6 years is a S-matrix bootstrap for in D larger than 2 dimensions. So you don't have integrability in D larger than 2 dimensions, but you do have constraints such as analyticity or unitarity. So you can apply S-matrix bootstrap beyond perturbation theory. And this is, of course, what Jeffrey Chu tried to do in the 60s when he started dreaming about S-matrix bootstrap for the first time. But at the time, not much success has been achieved. Well, actually, some success has been achieved by André Martin and others. But nowadays, there are people who push it and try to perhaps solve scattering of QCD particles using these techniques one day, like pions, protons, and so on. So it would be really interesting. And okay, there are some other applications of surprising applications of Bootstrap philosophy in things like matrix models, which are really recent and are really interesting. But okay, I'm not going to talk about this today. So cannot. So let me go then to the focus of my talk, CFTs in D larger than 2 dimensions. So what makes these systems an ideal arena for applying the Bootstrap philosophy is that, on the one hand, they're encoded rather economically. So every CFT in flat D-dimensional space is encoded just by a set of numbers, which are, so there are 2 sets of numbers. One set is the spectrum of primary operators, which are characterized by their scaling dimensions, just real numbers, and some representations under global rotation group, SOD. And then there is OPE coefficients. So you have a convergent OPE in a certain region, and you have this OPE coefficients of structure constants, which are again some real numbers, times some coordinate dependent factors fixed by the symmetry. So these numbers, Fi, Jk, and delta I, they characterize your theory, your conformal field theory. There are some constraints from unitarity saying that these numbers, delta I, they cannot be too small, and these numbers, Fi, Jk, have to be real. So there's a very economic set of numbers that you have to determine. And then there is this complicated constraint, crossing constraint, which says that if you take a 4-point function and you expand it in the so-called S-channel conformal block expansion, which corresponds to exchanging operators in between 2 pairs of fields, external fields, and you can also exchange the operators between the other pairs of external fields. And in a certain region, you can show that these expansions converge in some overlapping region of convergence, and so they have to agree. So this is a non-trivial constraint. This is a highly non-trivial nonlinear constraint because the conformal blocks are some nonlinear functions of scaling dimensions. The OPE coefficients enter as products. Well, it's a quadratic on OPE coefficient, so you have to solve it. And yeah, so it's nonlinear number of infinite number of constraints on infinite number of coefficients, so hard to solve. But you may try. And if you do it, then this is the Bootstrap philosophy. And again, this idea was, I mean, it's not a new idea. It's been around since the 70s, but people were stuck for a long time because of the following difficulty. So in fact, it's present, and this difficulty has been realized in the first papers on the Bootstrap by Polyakov in the 70s and so on. So the difficulty is that these 2 S and T channel conformal block expansion, they work best in 2 different regimes. So if you parameterize, you can, I'm not going to bore you, but there is some variable z, which is parameterizes the distance between operators in the S channel, and then 1 minus z parameterizes the distance between the operators in the T channel. So the S channel expansion converges when z is small, and the T channel expansion converges best when 1 minus z is small. So so it's kind of difficult to compare these 2 expansions because if you take an individual conformal block in the S channel and you would try to compare it with what you get in the T channel, then you see that it just doesn't, one conformal block won't do it, because individual global conformal blocks, they only have logarithmic singularities in the T channel, and but you expect a power-like singularity, and so well, this is not necessarily a paradox. It just means that you have to sum infinitely many blocks to reconstruct the T channel power law singularity. And this was known for the first people who worked on this. You know, it definitely was known to Polyakov. It was known to Parisi. I talked to these people just for fun. And yeah, so you have to do something. And okay, and in 2 dimensions, it works very differently because the Virasoro blocks, they actually do have a power law singularity in the T channel. And so that allows for the existence of the minimal models where you exchange only a finite number of Versor blocks, but nothing like that exists in larger than 2 dimensions. And so because of this difficulty, well, there are various strategies to deal with this difficulty, and I'm going to explain them. So there is a numerical strategy, there are some analytic strategies, so I'm going to talk about them. Any questions? So people who are uncomfortable with asking questions by interrupting me, they might also ask questions in the chat. Maybe I'll see them and I'll also try to comment on them. So the first strategy is that, well, it's a very simple strategy, but somehow it didn't occur to anyone but for the first time before us. So just, okay, the first channel works at small z, the other one at large z. So why don't we just work at middle point z equal 1/2? It's a very natural middle point where both channels converge. So they don't converge as fast as at smaller z, but they do converge. Actually, they converge exponentially fast, as you can show. And so you compare the two channels, you decide to compare them where they both converge at middle point. Seems like a natural thing to do. So this strategy, it has several advantages and disadvantages. So because, as I say, both channels converge exponentially fast in this regime, it means that you are basically going to be sensitive to operators with the small scaling dimension, because the contributions of operators of large scaling dimension, they will be exponentially suppressed around this point. So yeah, you will not have very good sensitivity to those operators of your conformal field theory. But you might not be interested in those operators anyway, because most interesting operators of any conformal field theory are operators of small, arguably operators of small scaling dimensions. They're phenomenologically the most interesting operators. Relevant operators, and maybe stress tensor, okay, she also has dimension close to 1, and maybe the leading irrelevant operators. So these are phenomenologically the most important operators. So this is an advantage. I mean, this might, depending on your perspective, might be disadvantage or advantage, because maybe someone is really interested in operators of large scaling dimension. Okay, what I would call a disadvantage is that if you work at z equal 1/2, you have this interesting thing that there is not much structure at z equal 1/2, because you have conformal blocks. Conformal blocks, they are at best some hypergeometric functions. In some more complicated situations, they're not even known in closed form. So at z equal 1/2, they're just some complicated numbers, nonlinear depending on scaling dimensions and everything. So, and somehow they have to conspire so that crossing is satisfied. So crossing is going to be satisfied by canceling all these conformal blocks against each other, and they're going to be basically many independent looking terms which have to cancel to conspire that crossing is satisfied. There's really very hard to see what's going on if you try to do work analytically, for example. Well, yeah, so you will be dealing with hypergeometric functions at z equal 1/2. It really doesn't, we don't really have much intuition about these numbers. But if you say, okay, but I just want to understand what's going on, then you might still work numerically, and this is going to be possible. And it's going to be systematically improvable. So you can push to higher and higher expansion around the z equal 1/2 point. It's not difficult. The higher you push, the more stronger the constraints are going to be. And once this has been done, some miraculous results were uncovered, which were completely unsuspected before this was attempted. And these miraculous results, they, well, I mean, they are experimentally relevant. They give you some numbers that you compare to the experiment. but they also point at some hidden structure in these problems. So it might be that actually, well, so these things that you initially found numerically, they may have some eventually analytic explanation, and maybe there is some integrability structure at the end, which people don't really understand at the moment. So there are many people in France interested in integrability, but they mostly work on N=4 super-Yang-Mills and things like that. But okay, maybe one day, if they have time from solving N=4 super-Yang-Mills, they can look also at this problem, and their expertise in integrability might be useful in trying to understand what's going on. You know, Volodya Kazakov always bugs me that you know, this is all numerics and so on, but you know, I'm saying you are the expert in integrability. It's your responsibility to tell me what's going on here. So let me show just you a few examples of these interesting things that can be done using this strategy. So the first example is what happens if you take a three-dimensional conformal field theory and you impose several constraints such as unitarity, Z2 global symmetry, and you assume that there is only two relevant scalar operators, which you call sigma and epsilon, with this quantum number. Sigma is Z2 odd and epsilon is Z2 even. So all other scalars are larger than 3 scaling dimension. And then you ask, okay, which values of delta sigma and delta epsilon are consistent with crossing? Because crossing, of course, involves all dimensions of all the other operators, all OP coefficients, and so on. So you have to take this all into account if you are carefully doing computation. But now, once you took it into account, you marginalize over all this extra data because you need to show some two-dimensional plot. So I want to show you a two-dimensional plot of a region where you can find all this other part of the CFT data where the crossing is satisfied. And it turns out, so this was found in this paper, actually in some earlier papers, but okay, this is the most careful study, that this region consists of two kind of disconnected components. There is a big disconnected component, which is not so interesting for today. And then there is a tiny island, which, okay, at the current level of numerical precision, it has size about 10 to the minus 6. And it keeps shrinking if you increase precision. If you increase the number of bootstrap constraints that you impose, it keeps shrinking. And the position of this island agrees, for all we know, it agrees with the position of the critical point of the three-dimensional Ising model. So the infrared fixed point of this non-supersymmetric RG flow of the lambda phi to the fourth theory in 3 dimensions. So this is what I call pretty miraculous, because this plot has been obtained by imposing just 3 crossing constraints for these 3 correlation functions: sigma, 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 epsilon, 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 epsilon. And moreover, you know, each of these constraints is a functional equation. So it contains kind of 3 times infinity number of constraints. So this infinity is being truncated to a finite number to do some numerical analysis, and then you get this plot. So what does this mean? Does this mean that the 3-dimensional Ising model is integrable in some sense? Why is it constrained so strongly by just such a small set of bootstrap equations? We don't know. So that's kind of a thing which came out of this analysis. So people have not suspected that the 3-dimensional Ising model can be amenable to this sort of bootstrap analysis before our work.
Slava?
Yep.
Great. What is the status of, and what is your opinion of, the other region?
Well, the other region contains other CFTs, some of which have been identified, because your CFT, so the Ising model has Z2 global symmetry, and it doesn't seem to possess any other symmetry unless somebody discovers some weird integrability. But there are other CFTs which have a bigger, which might have a bigger symmetry, but they have some subsectors which only have a Z2 global symmetry, and then they will show up in this plot. So for example, the n=1 supersymmetric three-dimensional Ising model, it appears in this plot for some conspiracy because it has some parity symmetry which can play the role of Z2, and so it sits somewhere in this region. And there might be other CFTs which sit in this region. So this has not been systematically studied.
And that kink, that corner.
No, it's not really
significant or no?
Yeah, it's not really a kink. It's this region actually has not been studied very carefully, and it's, you know, while this island, for example, the position of the island is completely stabilized, it just decreases in the size. This region, it kind of, if you increase the number of bootstrap constraints, it keeps kind of shrinking. So we don't really know what is the actual boundary. It has not converged.
Got it. Thanks.
Yeah. So there was a similar question of Boris about the big yellow wedge. Yeah. So we really know that the Ising model doesn't live there because we know, you know, we know a little bit the scaling dimensions of the Ising model from other techniques, from Monte Carlo, from epsilon expansion, and they like, if you take all those techniques, then you get some small square around the Ising island. It's small. It's not as small as the island, but it's definitely small enough to separate the island from this continent.
Slava, can I ask a question?
Yeah.
Hi. Is there a proof that, I mean, I understand it's a completely academic question, but is there a proof that a CFT actually exists in here? Like an analytic proof in the sense of...
No, there's no proof.
Okay. Is that interesting?
I think it would be interesting to devise some sort of fixed point argument, which, for example, would say that if you solve the equation, bootstrap equations with some finite precision, then you can always upgrade this approximate solution to an exact solution, but this has not been done as far as I know.
Okay. Thanks.
Because like this, it's kind of weird because we know that by increasing precision, this island is going to shrink, but maybe it would be a bit disconcerting if by increasing precision, for example, it would just completely disappear. In fact, it's known that at least in some cases, for some other theories, this may happen because there are some other theories which are slightly non-unitary. There are some conjectured CFTs which are slightly non-unitary. So if you just try to study them using numerical bootstrap, then you're going to get some islands maybe, and if you don't push the precision too much, by slightly non-unitary, I mean that their scaling dimensions are not real, but just a little bit complex, or their OP coefficients are just a little bit complex, maybe. But if you push in numerical precision, at some point those islands should just disappear because the CFTs don't really, because the numerical analysis assumes the exact unitarity, and those CFTs don't believe to exist as unitary theories, so they should disappear. Well, for the Ising model, we don't believe that this should happen. We believe that the island is not going to disappear, it's just going to shrink, shrink, shrink.
Yeah, I understand.
Yeah. But this has not been done. Thanks, Peter, for the question. Okay, but let me then discuss another example, which is maybe more interesting for this audience because it has something to do with supersymmetric field theory. And so this in this particular example, I consider n=2 three-dimensional supersymmetric Wess-Zumino model with this superpotential, which has a cubic with there are 3 chiral multiplets, and there's a cubic coupling x1, x2, x3, and there is another cubic term x1 cube plus x2 cube plus x3 cube. So I choose some combination of couplings which preserve permutation symmetry of these 3 multiplets, so that there are only 2 couplings, complex couplings h1 and h2 in the superpotential. And so this n=2 Wess-Zumino model, it flows to n=2 SCFT in infrared. And since I have this 2 couplings h1 and h2, there is actually a conformal manifold. So there's an exactly marginal deformation, and so it's there's this coupling tau, which is the ratio h2 over h1, which lives in CP1, which parameterizes this conformal manifold. And because of some discrete symmetries, the actual moduli space is not CP1, but CP1 over S4. So there's a fundamental domain. And so now, why would you like to bootstrap this theory? Well, because from exact SUSY prediction, you, for example, know the scaling dimensions from our symmetry. You know the scaling dimensions of this chirals in the infrared. For example, you know that xi is 2/3, has scaling dimension 2/3 in the infrared. Xi xj, again, is a chiral primary, has dimension 4/3. There are some other things that you can compute exactly about this theory. For example, you can use localization techniques to predict the 2-point function of the stress tensor of this theory. But there are some other things which are unprotected by supersymmetry. For example, there are non-chiral primaries of the schematic form xi xj bar, which are not protected. And so you might wish to bootstrap them because you know so much about the theory. So you know xi's dimension, Well, for example, for the Ising model, you didn't know dimension a priori, you didn't know the dimension delta sigma, delta epsilon. Here, it's like you know already dimension of delta sigma xi, but you don't know the dimension of some operators which appear in the OPE, xi times xi bar. But you might want to determine the dimension by bootstrap or see what the bootstrap says about these dimensions. And you might also want to do this as a function of this coupling tau, because they should have some non-trivial dependence on tau, these scaling dimensions of xi xj bar. And now you have to think a little bit how to incorporate this tau in the bootstrap analysis, but in fact it can be incorporated through some chiral ring relations. So there is in fact, out of many chiral primaries that you can construct by products of xi's, some of them are not going to be present because of the chiral ring relations falling from the superpotential. And so these chiral ring relations, they involve this parameter tau. So this is going to be your way to input in the bootstrap analysis where on the conformal manifold you are. So this can be done. Actually, there is a nice paper by Baggio, Bobev, Chester, Lauria, and Pufo in 2017, who did exactly what I described. So they incorporated all they knew about these theories from localization. They incorporated the knowledge of superconformal blocks, because of course, if you are a professional, if you do bootstrap analysis for a SUSY theory, you shouldn't do it in terms of global conformal blocks, you should do it in terms of superconformal blocks. And they compared their bootstrap results with what they could obtain using the epsilon expansion. Because this theory, you can do the epsilon expansion in 4 minus epsilon dimensions, you can extrapolate to epsilon equal 1. I think you go to sufficiently high loop order, maybe to 3 loops or 4 loops even. And so in this plot, which is taken from, which I took from their paper, you can see the comparison between the dashed. So there are several operators which they plot in this paper. or in this plot, so there's like delta 1, delta 2, delta 2 prime. So all these operators are not protected. So this, they want to bootstrap them. There are some points of enhanced symmetry where some things are known exactly. If you apply the epsilon expansion, they get, for example, these curves, these dashed curves for the dimension of these operators after some Padere summation, whatever. And using the bootstrap, so in this paper, they did not obtain islands, but they just obtain upper bounds on dimensions of the operators. So the solid curves are the upper bounds on dimensions of these operators from the bootstrap. And you can see, well, you can see several things. So you can see that somehow, so in many cases, the shape, in all cases, actually, the shape of these curves is quite similar to the curves which are obtained from the epsilon expansion. And, well, it seems to suggest that if they were to push the numerics, then somehow this supersymmetric field theory would live on the boundary of the allowed space. So by just maximizing these operator dimensions, they could get these operator dimensions. So that's kind of another mystery of the miracle of the numerical bootstrap, which has not been suspected before these things have been done, is that many interesting things, many interesting theories seem to saturate bootstrap bounds. So there are some theories, of course, which live in the bulk of the allowed space, but like usually, by and large, if you try to maximize something, you will probably get something interesting. It's kind of weird. Not really understood why. I mean, there are some hand-waving explanations why you might expect this. People try to rationalize it, post-rationalize it, but this has not been really explained, I think, satisfactorily. Okay, well, now let me move on to the second strategy. So I mentioned that the first strategy to deal with this difficulty that it's hard to connect the cross and the cross channel and the direct channel is to work at the midpoint, is one strategy. And there is another strategy which actually says, well, I'm actually going to try to do what Polyakov didn't manage to do, which is to connect directly, start from Z small and try to connect to Z large. Large meaning close to 1. And you will have to deal with infinitely many blocks. But as we will see, this is both a complication and a bonus, because you will learn something about infinitely many primaries of your theory in one go. But there's a little twist to the story that Polyakov didn't know, and this was realized in these papers, is that if you want to do this kind of efficiently, you have to work in the Lorentzian signature, because in Euclidean it's just too much of a mess. There's all these infinitely many blocks, they completely mess things up. But you can separate this mess somewhat if you work in the Lorentzian signature. So you have two parameters, Z and Z bar, and the Lorentzian light cone limit corresponds to Z going to 0, but Z bar going to a constant. So that's it became known as the light cone bootstrap, this kind of analysis. And as people might know, in this Lorentzian light cone limit, you are sensitive to operators not at small scaling dimension, like I was saying, the Euclidean numerical bootstrap was sensitive to operators at small scaling dimension, but you are here going to be sensitive to operators at small twist, which is the difference between dimension and spin. And actually, naively, when first this was proposed, it was supposed to work in the limit of large spin and order 1 twist, but somehow with various improvements, this technique works reasonably well even to spin of order 1. So it's really nice. And what you learn if you do this analysis is that you learn that operators in the conformal field theory in D larger than 2 dimensions, you learn that there is some organizing principle, that these operators organize in families which are called Regge trajectories. So it's kind of similar to CFT to string theory Regge trajectories, except that they are not they're not straight, they're curved. You have some complicated analytic structure. And also in this technique, since you kind of work in the small z limit, where things are nice and analytic, you can actually do analytic computations. And you get some results. You don't have control over rigorous error bars, unfortunately, not yet in this way of doing things, but the results you get, they agree with numerics pretty well. So there's some hope that maybe in the future there's going to be some synergy between this approach and the purely numerical approach. So basically, in this Lightcomb bootstrap, the idea is that, okay, as I said, there's this two variables z and z bar, and in numerical bootstrap, you work in the middle of z and z bar equal 1/2. And in the Lightcomb bootstrap, you work along this boundary of the causal diamond, where z goes to 0, but z bar stays finite. And okay, I'm not going to explain how this works, but the typical result that you can obtain is that you can show, for example, that any conformal field theory in D larger than 2 dimensions, if you take an OPE of two, for example, scalar primaries, then in this OPE, you should find an infinite family of operators that we can denote OL of even spin. I'm just giving the simplest result of this kind. You can generalize it in various ways. And the dimension of this operator's delta, it has to go as spin plus twice the dimension of the field phi you started with. So there's this finite intercept of the rigid trajectory. And there is some correction, 1 over L to some power, that you can predict the size of this correction pretty well in terms of various other pieces of the CFT data. So this correction is very well known. And so it's indeed, it's indeed pretty amazing, because there is infinite families of operators which live on rigid trajectories. So you might want in the future parameterize your CFT data not in terms of individual operators, but in terms of this rigid trajectories, which is more economic. So there's a lot of work about this, trying to get mileage out of this idea. And okay, so when this was proposed, it was observed that initially that this structure is very reminiscent to ADS physics. So in ADS, in theories with ADS duals, these operators exist. They're called double trace operators. And this correction to the scaling dimension can be seen in ADS as due to some gravitational effect of two particles in ADS being attracted to each other. And so this result that I'm explaining you, it says that basically any CFT in D larger than 2 dimensions, in some sense, it behaves similarly to these ADS theories, even though it might not necessarily have large central charge or large N. There is some similarity in the sector operators of large spin. Okay.
Slava, sorry, I have a question.
Yeah.
Sorry. So you mentioned it's a correction in 1 over L, 1 over the spin, so it's large spin. But the correction you mentioned is more 1 over N. Why is there a relation between the two? If you have an ADS dual, I mean.
Well, if you have ADS dual, there are usually the kind of pictures that people draw is that you have ADS space. You have two particles in ADS space, and if they rotate around each other, so that to get an operator of large spin, you have to make these particles rotate around each other. And then you measure the correction to the energy of this two particle state due to gravitational interaction. And then it will scale as there's going to be Newton constant. There's going to be some factor of the Newton constant in front, but there's also going to be 1 over L dependence.
Okay. Thank you. Yeah.
And okay, and interestingly, this beautiful rigid trajectory this result that I explained about the existence of these families of operators, it's only true in larger than 2 dimensions, because only larger than 2 dimensions, you have twist gap between the stress tensor operator and the unit operator, while in D equal 2, there's no twist gap. And so you can derive similar results also in D equal 2, but they look different and they are not as easy to interpret. And okay, this is the plot which shows how beautifully this numerical and light cone bootstrap, they agree with each other. So in this plot, the dots, they denote the spectrum of operators extracted purely from numerical analysis, just which works around z equal 1/2, but goes to very large derivative order. So in fact, it is sensitive also to, you could say, to larger space of part of the ZZ bar space. And the solid curve is a prediction for what this spectrum should look like for this particular family of operators. And the solid curve depends on just 4 numbers. The dimension of operator sigma in 3D easing, epsilon, and a couple of OP coefficients. And it agrees very well. So it shows that there is some harmony in this numerical bootstrap spectrum. Okay, so one thing which needs to be mentioned is that this light cone bootstrap, it went through several kind of technological improvement stages. So it was first indeed proposed as a sort of bootstrap technique where you compare the 2 channels working close to the light cone. But then it has been, there was this interesting development called Lorentzian inversion formula by Caron Hua in 2017, so it's a sort of integral formula which takes a 4-point function of a CFT. You know, you consider something which is called double discontinuity, then there is some integral kernel, you do this integral over ZZ bar in the Lorentzian space again. And you define some function of 2 variables, delta and del, but now this is a L doesn't have to be an integer. So it's an analytic function of delta and an L and of L, at least in some range of deltas and dels. And the claim is that this function C delta L, it has poles at the position of the actual, if you take L integer and vary delta, then this function C delta L, it has poles where the CFT spectrum is, and the residues of the poles are OP coefficients squared. But now, since this is an analytic function, you could say that this explains kind of why there are these rigid trajectories, because it explains why CFT operators want to live on these analytic curves. And it also amazingly simplifies this light cone bootstrap analysis. It's really a machine which allows you to derive all these results that have been derived by some complicated calculations very easily. But said that, I should add that, so there is this nice agreement between numerical analytic bootstrap, but there is also a small kind of question mark that these analytic techniques, they are actually, it's not always clear whether they're, well, they have not been justified, let's say, at the same level of rigor as the numerical bootstrap analysis, because numerical bootstrap analysis is really based on very small set of rules. And here, when you apply these techniques, you have to make all sorts of assumptions about the analytic structure of various functions and in the Lorentzian space and integrals. And it's not clear if these assumptions, they are valid for all CFTs or just for some CFTs. They're definitely valid for some CFTs, like they seem to be valid for the 3-dimensional easy model, and they're valid in perturbation theory. But it would be interesting to understand better the relation of this. It would be interesting to justify various steps in this derivation more carefully. And and this is not only interesting, but this is very important if one day we would like to put these two approaches together. If we would somehow like to have a hybrid approach which mixes numerics with analytics, I think it would be very important.
Indeed, a very naive question, sorry again.
Yeah.
Is it valid for free CFTs, this reconstruction formula?
For free CFTs, it's valid. Yeah, it's very easy to. For Gaussian CFTs, it's a very easily
The generalized free, I mean.
Yeah.
Okay.
It's in many cases where it's checks, it works very nicely, but there is some magic out there because people have not carefully checked all the steps, and so people kind of are very excited to apply this new machine, but haven't yet fully understood what's under the what's in the engine compartment.
Yeah, thank you.
Okay, and so actually, I'm a bit out of time. There was because I prepared 1 hour. I didn't know it was supposed to be 50 minutes, because I wanted to discuss briefly at least one more analytic approach, which is both analytic and rigorous. I don't know. Do you? I have like 3 transparencies.
Yes, actually, there have been some questions during the talk, so I think you can. Go.
Okay, thank you. So this is something which is called analytic functionals, and it's been developed by Daniel Mazic and Miguel Paulos in École Normale. And so I am going to consider the simplest case of this approach, which is in one-dimensional CFT case, where there is just one variable z. And the bootstrap equation that you want to analyze looks like some sum of PD, where some positive numbers times some functions f delta, sorry, where delta is the scaling dimension of the operator, and it represents the difference between S-channel and T-channel conformal blocks. So f delta are some known functions of differences of conformal blocks. And the functional, what we mean by a functional, we mean something which is a linear thing which acts on functions, maps functions to real numbers, such that if you take such a functional, you act with this functional on the bootstrap equation, and you get an equation which is now a numerical equation. So sum of p delta alpha of f delta equals 0. And both numerical and analytical bootstrap, they use with functionals. So in the numerical bootstrap, the functionals that you use are some finite linear combinations of derivatives of this f at z equal 1/2. So that's what I wrote here. So you vary this coefficient Cn, they are at your disposal. And by varying these coefficients, you try to make your functional, if you plot this alpha of f delta, then you try to get some curve which at large delta is always has to be positive, and then somewhere it will necessarily kind of pass through 0, and then it just life is such that it will always happen. And then at delta equals 0, which is the unit operator, you also want your functional to be 0. And so if you manage to find such a functional, which means that you manage to find such coefficient Cn, then because these coefficients p delta are always in unitary theories, they are non-negative, it means that somewhere in this range between delta equals 0 and delta equal delta star, your CFT must contain at least one operator. Because if all operators were above, then you would get a contradiction, sum of positive numbers equals 0. That just doesn't work. So that's the numerical bootstrap. But now, if you take the numerical bootstrap and you increase the numerical, you increase your numerical precision, which means you increase this parameter n in your numerical functional, then you might get something which looks like, it's going to be a functional which maybe will have not only will it pass from negative to positive, it will have maybe a bunch of double zeros, but then eventually, since if it's made of derivatives, then it will always grow at large delta as polynomial. And then you think that there should be some hypothetical, so-called extremal functional, and it was introduced by Rychkov and Paulosh, which doesn't do that, which kind of, it passes from negative to positive, but then it just only has double zeros. It keeps oscillating, but it never grows. It never starts growing as a polynomial at large delta. It just has an infinite number of double zeros. So if such a function exists, okay, it should exist, but if it exists, it cannot be made as a finite sum of derivatives. It should be a more complicated linear function. But there are many other linear functionals that you might consider. And it is these functionals that have been constructed by Mazach and Paulosh. They constructed a particular family of such extremal functionals which have integer spacing of zeros. And their functionals, they indeed are not linear combinations of derivatives, finite linear combinations of derivatives, or if you wish, they are not finite linear combinations of derivatives, but they can be written in a nice way as a contour integral of f against some function h of z. And so having such functionals, you can do many beautiful things. You can, for example, prove analytically certain numerical bootstrap bounds in d equal 1 dimensions, but also people are trying to generalize this to d larger than 1 dimensions. And yeah, there are many interesting applications of these ideas. But why is this particularly interesting is that because I told you that any CFT in this second part of my talk, where I talk about Lightcomb Bootstrap, I said that CFTs contain these families of operators where delta grows as spin. And so if delta grows as spin, then it means that asymptotically the spacing in the spectrum becomes integer. And so the zeros of these functionals, they in fact correspond to the position of operators in the spectrum of your theory. Of course, we don't expect on some boring theories have integer spacing, but even non-boring theories like 3D Ising model, they have asymptotically integer spacing. So people hope that by using these functionals instead of derivatives, maybe you can have they provide a better starting point even for analyzing interesting theories. So that's maybe what I want to say about this function. So there are some things that I have not covered about the Bootstrap because there are many other topics, but I think since I'm out of time, I'm going to stop here, and thanks for listening.
Okay. So let us first of all thank Slava for a wonderful and pedagogical talk. So we have still several minutes for questions, comments. So please. Maybe I will start then by a very naive question. So I'm curious about this three-dimensional Ising example. So is the numerical precision good enough as to guess the exact answer for conformal dimensions?
No, not yet. Well, in fact, people have tried to make some guesses. If you just take the 3D Ising, then you don't get using this database. You mean we know that there's this magic database. If you plug in the digits, you don't. If you just plug in Ising, you don't get anything particularly interesting. I mean, you get many things that can fit. But if you plug in both Ising and the supersymmetric Ising, which exists in 3D, And then you kind of look at formulas. If you make a selection saying that, okay, I would like a formula which looks the same for the easing and for the supersymmetric easing, it's the same, meaning made out of the same general things. Then you do get some. Then you do get something interesting, which is made out of gamma functions. So you get some things which are made out of gamma functions of k over 24, some linear combinations of these gamma functions, something like. I forgot what are these numbers, but it's a rational function of gamma over k over 24. Again, some gamma plus or minus gamma with some coefficients. And well, people, in fact, one of the motivations for trying to push the numerics a bit further is to see if indeed this formula, for some reason, turns out to be correct. But I think people are, well, people are not hoping too much that it will be correct, but well, who knows?
Mm-hmm. Thank you. Any other question or comment?
If I may.
Okay.
Sorry, no. I had the question already. You go ahead.
May I ask a question?
Sure, Sergey.
Hi, Slava. Thank you for a nice talk.
Hi.
On this slide which you have, you mentioned boundary defects CFT in high ID. There are some interesting CFTs which are free in the bulk but interacting on the boundary. Did anyone study such this kind of theories from your perspective?
Yeah, there was some work about this kind of theories, maybe not exactly the ones that that you have in mind, but there was some work by about something that is basically GFF, generalized free theory, which you can represent as a free theory by adding extra dimensions.
Mm-hmm.
And then you add some perturbations on the boundary, like 5 to the 4th, for example. Such things have been studied in Bootstrap. It's kind of interesting because indeed the fact that these theories, they have this separation bulk boundary, they allow you to predict exactly some quantities, and then, as you've seen in, for example, in this supersymmetric example, if you predict exactly some quantities or some relations between OP coefficients, then you can put it to good use when you bootstrap the theory. And this has been tried, but there's not too much work, I would say, in this direction. Yeah.
May I ask you another question? Conformal anomaly somehow appears plays some role in Bootstrap program.
So conformal anomaly is a nice quantity. So conformal anomaly is encoded by OP coefficients of the stress tensor, by 3-point functions of the stress tensor, and if you bootstrap 3-point functions of 4-point function of the stress tensor, then you will be able to input the values of these conformal anomalies, or you will be able to bound these conformal anomalies in terms of other things. And this has not been done in 4D. There was a Bootstrap study of the 4-point functional stress tensor in 3 dimensions, where you have a similar structure in the 3-point functions of the stress tensor, though in that case maybe you would not call those OP coefficients anomalies. And in that case, there's some interesting interplay between the values of these coefficients and other parts of the data of CFT data. So this has been studied, but in 4D not yet.
Okay, thank you.
Okay, thank you very much. I suggest that we stop the discussion so that participants could have a break to prepare themselves for short talks. So we resume at 11. Boris have just sent you the link to the virtual space for discussions. And so many thanks once again to Slava for this nice talk.
Thanks, Slava.
If there are further talks, I'll try to join this Gather Town and see how it works. So if there are further questions, I mean.
Sure. If I wanted to ask about the Lorentz inversion formula. So if you have 5 more minutes to spare.
Yeah, I do have more 5 more minutes, but yeah, should we talk here because Oleg wanted to close the session, and I don't know what.
Yeah, I think that already we can stop the recording.
Yeah.
Right.